Bit of advice on intermittent fillet welds. These are usually painful for people to do. Lots of people don't like to do them because you have to mark it out. You've got lots of starts and stops. Painful, so sometimes people would just simply prefer to do a continuous weld. And I'm just amused by the Eurocode here because it kind of says that we need to account for the fact that we've got bits of weld missing when we work out the resistance, which I would have thought would have been patently obvious, but there we are. The Eurocode has reminded us that we need to do it. I started off when we got into the technical aspects of welds saying that welds are not really very ductile. So you would be ill-advised to assume a plastic distribution in your weld group. I would commend to you an elastic distribution, however you're envisaging it, because otherwise you are relying on ductility, and welds are notorious for not being ductile. And this is what the Eurocode says: ductility of the welds may not be relied upon. Not sure what else you would rely upon, but certainly stick to an elastic distribution would be my recommendation in weld design. We often come across sort of welding things in sort of an out of plane direction, and we want to calculate the force on the welds. The classic way to do this is to assume a unit throat dimension, so just 1 millimeter, and work out the load on your weld in terms of a unit throat. So the little diagram on the top right hand side, maybe we've got welds across a flange, an incoming beam to something else. We've got some moment perhaps, or an eccentric shear which causes a moment. Well, it's just working out the second moment of area of that weld group. It's as straightforward as that. Nothing more to it. You could look in an old version of the Steel Designer's Manual, and that will give you exactly the value which I've just calculated. And then what are you doing? Well, you're just working out the vector sum. We've got a load due to the vertical shear, P. We've got a load due to the fact that that P is applied at an eccentricity. That's the red diagram, red arrow, I should say. And then we've got the vector sum, which is simply the green arrow on this particular diagram. If you've got kind of a torsional load on something, and sometimes we do, so a hollow section perhaps connected to an end plate, and we've got a torsion, that's why we've chosen a hollow section. We need to perhaps design the weld around the hollow section. Well, again, we work out the vector sum. So we have like a polar modulus, people might remember that term, a polar modulus of the weld group, just like we might have had a polar modulus of a bolt group. So again, we've got the same thing. We've got the vertical load P divided by the full length of the weld, and then we've got the moment divided by the polar modulus, and that will give us a stress, and then we'll just check that against the design strength of the weld. Those diagrams were from an old version of the Steel Designer's Manual. This is from the very latest version of the Steel Designer's Manual, so it's doing exactly the same. Over on the top right-hand side here, we're working out the two components, one a rotational one a vertical one, and then the resultant. The only thing which amuses me about this one is that I think the axes are wrong, so we don't have Y and X anymore, do we? We have Y and Z. But there we are. Everything else seems to be okay about the process. It does get rather more interesting, ladies and gentlemen, if you've got something really weird like this. So this is a three-sided weld. Imagine an angle being welded to a T cord of a lightweight truss. So we're looking at the stem of the truss. The angle is laying alongside that stem, and we're kind of welding all round it, maybe on three sides, maybe on four sides. But then you've got a really weird shape of a bolt group then, haven't you? Different lengths. We've also got some eccentricity, maybe because the centroid of the bolt group is not on the same position as the center of gravity of the angle. So if you do have to, or if you are asked to design for those situations, you probably need a bit of a spreadsheet to work out all those features, but you do exactly the same. You'd work out the polar modulus of the weld group. You'd work out the longest distance, which is shown in green, to the extremity of the weld group. So therefore you could work out the stress due to the moment being produced by the force multiplied by the eccentricity.